Okay, so we should get going. Lot to review today. So there is a test on Friday. It's going to be fun. I guess one quick announcement is that we finally got the course evaluation sent out. So we are up to 25%. So, but don't worry, we'll get there. We got another 2 weeks. So get those course announcements filled out. That's our goal, 80. We'll get there. Okay, so the test coming up on Friday is everything since the last test. And so it's been a while. We're a little rusty. We've missed having these nice tests. So we'll get back into the swing of things. So what are we going to talk about? Well, there's two major topics. This is page 1 of 2. This will be scanned in so you can get it online later on today. So we have basic integration. And what are things that you should be able to do? You should be able to set bounds, to change the order of integration, to work in polar, cylindrical, and spherical coordinates, be able to use symmetry, be able to do Jacobians, which is really just another way of saying change of variables, do line and surface integrals, and know applications, things like volume, surface area, mass, moment, inertia, and center of mass. So there's various bits and pieces here. I'll just point out well, maybe I'll try to get through these really quickly. So when we do these integrals, we always do integration when we want to get an answer out doing iterated integrals. And it's sort of nice to remember where we go between. So the outside integral always goes between two numbers. So you should never have functions on the outside. So we're going from like 2 to 4 or something. The next layer in, you're going between curves. So it's between curves in some plane. And then the third layer in goes between surfaces. So you should be keeping this in mind when you're setting up your bounds. How do you set up your bounds? Know what layer goes with what. Remember that integrals always have 3 parts: your region, your function, and how things break up. So make sure you know how to account for all of those. The hardest part, I think, is describing your region. You should be comfortable doing spheres, cones, planes, and cylinders. Those are the types of things that we usually use to describe shapes. Know things such as in 2 dimensions, dA is r dr d theta. So for example, if you're integrating in polar, if you have a problem involving polar. dv, which is dz dy dx, is r dz dr d theta, or rho sine of phi, d rho d phi d theta. Right? Easy. Know how to change bounds. Draw a picture, label everything, find your new bounds. Work from the outside in. That's how I do it. Other instructors will tell you work from the inside out. It doesn't, well, I mean, it's a convention. And as long as you get the right answer, we're okay. That's what we grade on. Do you get the right answer? We're not grading on, do you do it exactly like so-and-so does it? You know, that's not what we're after. We just want to make sure you do it in a right way. Know how to change variables. This is where the Jacobian comes into play. I will say that the hardest part about this is identifying the substitution. We will never ask you to do that. We will say, here's the substitution. And then once you have that, really it's just a matter of saying, let me take care of each of these 3 parts. What's my new region become? What's my new function become? How do I break things up? And to break things up, know how to use the Jacobian. Know how to do applications. We love all sorts of applications, but I will say a very popular one tends to be center of mass. So make sure you're familiar at least with that. We have put inertia in the past on exams as well. And know how to do line integrals and surface integrals. So if I'm integrating along a curve, f of x, y, ds, what do? I rewrite everything in terms of a parameterization. So I parameterize my curve. I have x of t, y of t. And my ds, I write square root of x prime squared plus y prime squared. If I have a surface, similarly, z equals f of x, y. The integral g of x, y, z, d of s, a. I rewrite my function, g of x, y, f of x, y. I change my bound, so instead of going over the surface, I go over my region, and my dsa becomes what we had for surface area. Okay, so that was the basics of integration. Any questions on this portion? Okay. It's easy, right? Now you look back like, oh, man, this isn't so bad. This is great. Cool. Then we had phase 2, which was saying, what happens when we do integration and throw in vector-valued functions? So you should know how to work with vector-valued functions. So in other words, we had this del operator, know about the gradient. Well, I really hope you know about the gradient by now. Know divergence and curl. Know about how to compute work. Well, there's several ways that we oftentimes write the same integral. So the integral f dot dr, it's the same as the integral of f dot t ds. It's the same as integral m dx plus n dy plus p dz. Know how to do mnp dot n through dsa. This is doing here is this is actually computing the flow through a surface. And that's one of the common applications we have is dealing with flux and flow. Now, what are the big ideas? There's 4 big ideas when it comes to vector-valued functions and integration. And you can bet that you will be tested on some subset of these ideas. And between this and the final, on most, if not all, of these 4 big ideas, you will see. So what are they? Well, one says if I have a curve going from some point A to some point B, and I want to integrate along that curve a gradient dot dr, gradient of f dot dr, then the answer is I actually don't care about the curve. Curve is not important. Well, why not? Well, it turns out it's f evaluated at the end minus f evaluated at the start. Doesn't depend on the curve. Now, the hard part about this is we don't usually tell you, oh, by the way, this is a gradient of something. You have to figure out, yes, it's a gradient of something, and here's that something. So you have to say, oh, for example, if I'm given a curve integral m dx plus n dy, how do you find f? And then we went up and said, okay, how about Green's theorem? And in Green's theorem, there was an orientation. And remember, everything now has orientation. So, for example, start to end. That's an orientation. Where do you start versus where do you end? Here, orientation is you orient. Some people say orient counterclockwise. It's better to say orient so that if you're walking on the curve, the region is to your left-hand side. To the left. To the left. When you walk the curve, keep the region to your left. All right. So what does Green's theorem say? Well, the integral around the curve m dx plus n dy is the same as the integral over the entire region, partial n partial x minus partial n partial y dA. And in essence, it's kind of similar to what's going on up here. It says, this is kind of like a derivative, and then I'm just evaluating the original function. Well, this is kind of like a derivative, and I'm doing more or less like the original function, but on the edge, on the boundaries. So it's a very common theme. Now, you can do 2 variations. So one variation is just to say, oh, this left-hand side is really f dot t, and this right-hand side, that's really a piece of a curl. And so f dot t on the boundary is the integral of curl of f dot k. It's that last third piece of the curl. Well, this generalizes to Stokes theorem. And Stokes theorem is essentially Green's theorem in 3 dimensions. It says, look, suppose you have a curve, and it's the edge of a surface. Well, you can either integrate along the curve of f dot t, or you can integrate on the surface curl of f dot n. So, first off, how do you know if you should be doing Stokes theorem? Well, one thing you should look for is, am I in 3D, and do I have a surface with a boundary? Then you're for sure it's going to be a Stokes theorem type question. But more generally, you should think of, well, what happens when I did Green's theorem? Green's theorem was if I had a curve, and then I had a region on the inside. And sometimes we didn't even tell you about the region on the inside. We just say, here's the curve. Same thing can happen in 3D. It's like, look, as long as you have a curve in 3D that's closed, there's a Stokes theorem that can come into play. Now, what we often do is we give you really terrible surfaces when you should be like, wow, what a terrible surface. Why don't you just use a nice flat surface? Well, spoiler alert, that's how you make it easy. Okay, so look, if you don't like the surface we give you, choose your own. Bring your own surface. That's perfectly fine. Just be careful. Orientation matters. Keep track of orientation. So you can think of, stand on the top side of the surface and make sure that you keep your region to the left. Also, right hand rule comes into play. So for all those people who've been practicing for the last, 20-some years with your right hand, now it's like, finally, this is the day where you get the curl of the fingers going in the direction of motion. Your thumb points and tells you which way is up. Thumbs up. Okay. All right. Now you know where that expression comes from. Thumbs up, right? You've always wondered. Okay, good. Now, other variation of Green's theorem says the integral on the boundary of f dot n ds. This integral is important. This is saying flow through the boundary. So the integral that computes flow through the boundary in 2 dimensions is the same as the integral in the interior of divergence. Well, it generalizes to divergence theorem, sometimes called Gauss's divergence theorem, which says the same thing in 3 dimensions holds. Which says if you have a solid, which, by the way, if you ever see the word solid, you should probably say, I wonder if divergence theorem applies. That's a big clue. So, integral of f dot n on the bounding surface of your solid. So the flow through the solid is equal to the triple integral of your solid of the divergence of your function. All right, so that's the big ideas. Any questions on these? Okay, well, I guess short class today. No, just kidding. Come on. Let's do some problems. Let's do some problems. Now, I have way more problems than I can possibly complete, so I may not complete all of them. I think it's better for me to go through and get things set up. Because once you get to a certain point, it's computational. And I believe in your abilities to compute. Or I hope I do. We'll find out. Okay, so these are problems from various old finals. And they may or may not reflect the content of the exam. Probably not, because I have 9 questions here. There's only 5 questions on the test. And but the hope, right? I strongly encourage you to look at the practice tests that we have written. And there will be 2. One from recitation and one that's posted. The one from recitation will be posted online on Thursday. So here we go. So rewrite the iterated integral 0 to 2, integral 0 to 4 minus x squared, integral 0 to 4 minus y, z square root 4 minus y dz dy dx as an iterated integral with order of integration dx dz dy, and evaluate the integral. I wanted to make sure we got one of these because people somehow, they don't like doing these 3-dimensional bound problems. So let's at least do one, see how it goes. Now, one thing is just sort of understanding what the bounds are. So notice this order here, if I go from in, so dx, dy, dz, that will match over here. So the outside is x, so I go x equals 0, x equals 2. Next is y equals 0, y equals 4 minus x squared. The last one is z equals 0 to z equals 4 minus y. That's making it really hard to read, but okay. So I like to understand my solid that I'm trying to sketch. Let me just make it clear about one thing. People who wrote the old finals, whenever they had a 3-dimensional problem, they didn't know how to draw 3-dimensional pictures, so they never gave you pictures. I have been learning how to draw 3-dimensional pictures. I'm not very good at it, but I promise you that any time you are in 3 dimensions, you will have a picture. You do not have to visualize. We are not testing you on your ability to see things in 3D. So if there's a problem in 3D, we will hand you the picture. Also because we know you don't get calculators, so it's a trade-off. All right. So what do we know? Well, we know x is going between 0 and 2, because that's what our outside integral says, and y is going between 0 and 4 minus x squared. Now, just these two in 2 dimensions, we can see what's happening. The curve y equals 4 minus x squared is an upside-down parabola, has here at 4, and comes down here to 2. And the reason I'm only drawing this part is this is indeed where x goes between 0 and 2, and y goes from 0 to 4 minus x squared. So this is y equals 4 minus x squared. Now, what happens is we have this third layer, 0 less than or equal to z, less than or equal to 4 minus y. So what I'm going to do is I'm going to now incorporate this picture into 3 dimensions. So I have x, y, z. So if I draw this here, I'd have x2, y4. So I have this curve down here. I'll do some little stippling here. So this right here corresponds to this region in the xy plane. Now, what do I have? Well, z goes from 0 to 4 minus y. What does z equal 4 minus y look like? Well, it's a line if I were looking in the yz plane. So if I just looked at the yz plane, oops, let me choose a slightly darker color of green. If I was looking at the yz plane, I would see this line here. But of course, this is a 3-dimensional picture, so if you see a missing variable, what it means is I'm just going to take that and copy it. So what will happen is I'm just going to copy this flat line straight across. Now, that would be, if I were going to do the whole thing, okay, you can imagine, kept it going forever. But I don't really care about the whole thing. I only care about what's over my region in the xy plane. So, my solid is this. It's the top part is this plane, z equals 4 minus y. This back side over here, that's the plane y equals 0. This back side over here, that's the plane x equals 0. The bottom side, that's the plane z equals 0. Then there's this curved face. Well, where does that curved face? Well, it's this curve right here. That curve is y equals 4 minus x squared. Okay, so that's my solid. Now, what am I going to do? Well, I want to set up a new integral. So, integral, integral, integral. Same function. Changing the order of integration doesn't change the function. But now, dx, dz, dy. So if I were going to set up this integral, the way I do this is I say, let me look down the x-axis, and I'm going to worry about x last. So if I look straight down the x-axis, I'm looking down this axis here, I would just see the yz plane. And if I look in the yz plane, what do I see? I see the triangle, which sits at 4 and 4. And this is the line y plus z equals 4. And now I say, well, this is easy to see. Now I say y. Well, y goes between 2 numbers. Okay, what are the 2 numbers? Low number is 0, high number is 4. 0 to 4. Okay, so that's my y bounds. Then I say, okay, what about z? Well, now I'm thinking about, I have a y, where does z go between? Up and down. Well, I'm going to go from the low value, which is z equals 0, up to the higher value. Well, I solve for z. Z equals 4 minus y. So 4 minus y. All right, now I come to my 3D picture. And now I need to solve for x. So where does x go between? Well, I'm going to go from the back side, and I'm going to move forward until I hit this front curve. So the back side is x equals 0. That's this plane in the back. The front side, that's that plane y equals 4 minus x squared. And remember, these are x bounds, so I need to solve for x. So I can write this as x squared is 4 minus y, or x equals square root 4 minus y. I don't need plus or minus because I want the positive part. And so that would go right here, square root 4 minus y. And now, dot, dot, dot. So that's the dot, dot, dot is the evaluation. But the hard part is just setting it up. So I'll stop there for this one. Okay. Now, let's try another one. Here's a really old one, an oldie but a goodie. Compute the flux of the vector field f of xyz equals xi plus y minus 2xj plus x minus zk across the surface of the solid determined by x squared plus y squared plus z squared less than or equal to 9 with the outward normal. Now I know what you're thinking about this kind of problem, and you're tempted to say, what, the flux? No, no, you don't think that. You just think, okay, what is flux? It's flow. It's flow. So how do we do this? Well, we remember, how does flux or flow get computed? It's that dot n integral. So when you talk about flux, that means the integral. Here's the surface of the solid. Well, surface of solid, usually, boundary of a solid, I'll use S for solid. And flux would be F dot n dSA. Now, by the way, I should note, this is my notation. Book uses sigma. Doesn't matter. So this is what it means by the flux. Now, what should we use to solve this problem? What tool? Give you a hint. Divergence theorem. Why? Because it's a solid. And because you're computing F dot n on a surface without a boundary. So in other words, it's a closed surface. There's no edge to that surface. So divergence theorem says that this would be equal to the triple integral over your solid of divergence of F dV. Well, one of the reasons we like this is it gives us a chance to test, do you know what divergence is? Well, let's test. Okay, so divergence of F. I come to the first term, and what do I do with it? Take derivative with respect to x, which would give me 1. Go to the second term, take derivative with respect to y, gives me 1. Go to the third term, take derivative with respect to z, gives me negative 1. Which means I'm integrating 1. Well, know your geometry. If you're integrating 1 dv, what are you computing? Volume. In general, if you ever compute 1 d something, you're finding something. So 1 d volume is volume. 1 d area is area. Well, what do we have? What is this shape? Sphere with radius 3. So sphere has volumes 4/3 pi r cubed. And you can cancel off a 3, 36 pi. And we're done. We're done. Yes. Okay, that one we actually finished. Cool. All right. We'll keep going. Now, spring 11. Actually, I think this, is this spring 11? This might be fall 11. Actually. Fall 11 is a sad tale, but I won't tell that story today. So, here we go. We have this problem. Set up an integral to find the volume of the solid that the cylinder r equals cosine theta cuts out of the sphere of radius 1 centered at the origin. Now, this is kind of hard to visualize what's happening here, but I'm going to do a terrible job of explaining. So you start with your typical, here's my unit sphere of radius 1 centered at the origin. Now, r equals cosine theta. What does that look like? Does anyone know? No? No r equals cosine theta junkies out there? It's a circle. It's a circle that looks like that. If you don't believe me, multiply both sides by r squared equals r cosine theta, then you get x squared plus y squared equals x, and then you work it out. It's a circle. So this is what it looks like here in the xy plane. So what's happening is, if I put that here, is that there's, wait, oops, did I draw in the wrong place? Oh my gosh, I did. Okay, pretend like I didn't draw that. Pretend like I drew it correctly. So what's happening is that there's this circle here, and you're boring it out of the sphere. So it's like you're taking a cross section of the sphere, and yeah, that's even worse. Okay. From above, if you look down from the z-axis, so here's from above. What would you see is so here's your x and your y. So you went and looked straight down. You would say, oh, there's this sphere here. And what I'm doing is I'm just looking at the part of the sphere that's just inside of that piece. So I'm taking that part of that sphere. Now the good news is it's not required to evaluate the integral, so we just have to set it up. Now, Okay, assuming we haven't confused ourselves too much, we have to think about how we would approach this problem. We're trying to compute a volume, which means we'll probably do some sort of a integral. So how can we compute volume? Well, one way to compute volume is that volume, if we remember our applications, it's the integral of height dA. So height times area is volume. So what can I do? Well, what I can do is I can say the following. Let's think about how we would integrate. If I'm here, what coordinate system should I be using? Polar. It's highly suggestive, if they hand you something in polar, that you use polar. Now, sometimes they will hand you something not polar, and you should use polar. Yep, you just have to think about your situation. Okay, so we'll do polar. dA is r dr d theta, and then we have height, which we'll have to figure out in a moment here. And then what do we have? Well, where does theta go between? Really? 0. What's it doing over here? Negative pi halves and positive pi halves. Yeah. Not everything has to go between 0 and pi. Where does r go between? 1 and 0? If it was going to 1, it'd be doing this. If only we had something with the form r equals to help guide us. Yeah! See? It's right here. 0 and cosine theta. Cool, 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 cool. Okay, now we've got our bounds. What are we missing? Height. Okay, now, let's think about height. Well, let's think about a sphere. We have x squared plus y squared plus z squared equals 1. Now the height is usually the z. So we solve. Z squared would be 1 minus x squared minus y squared, or z is plus or minus square root 1 minus x squared minus y squared. So, what does this become? Square root of 1 minus r squared. Is that it? I don't think that's it. I can't help but notice that there's a suspicious gap here. What? Times 2. Why times 2? Because there's a top of the sphere and there's a bottom of the sphere. Remember, the sphere has top and bottom. And we're cutting it out. So you didn't say just the top half of the sphere. Yeah, we probably would just take off 1 point for that too. But we're picky. We want right answers. People get upset when we take off points for wrong answers, but it's the thing that we do. It's the thing that we do. Okay, spring, 2010. Find the center of mass of the solid inside the sphere, rho equals 2, below the cone, phi equals pi thirds, and above the plane, z equals 0, if the density is proportional to the distance from the origin. Use symmetry where possible. Now, before we start, is there anything about this problem that tells us what kind of coordinate system we should be using? Yeah, we should definitely be using spherical coordinates because you see things like rho and phi. Those are nice things for spherical coordinates. Okay, and z equals 0. Well, we can translate by this way. What's another way to write the plane z equals 0 in terms of spherical coordinates? Phi equals 0 in spherical coordinates is, yes, phi equals pi over 2. Remember how spherical coordinates work? Straight up is phi equals 0. Straight down, phi equals pi. And halfway in between, this is phi equals pi over 2. So it's phi equals pi over 2. You can think of it as the xy plane is like a really, really, really flat cone. Because phi equals an angle is a cone. And so, for instance, phi equals pi over 3 is sort of this kind of cone, where this is the angle pi over 3. All right, now we actually are pretty close to drawing our shape. We might as well finish it off. So we're below the cone, phi equals pi over 3. And now I've noticed that I've said phi and phi both times in this same problem. I should work my way and get the pho and the fum out of the process there. So, okay. So we've also got this sphere here, but we're going to sort of cut it off. So this is a sphere rho equals 2, which is just, a sphere with radius 2. Okay? So it's sort of like we took the top half of a sphere and drilled a cone into it. Okay, so there's our shape. Let's talk about our various bounds. So if we were setting this up, what was dv going to be? Rho sine of phi d rho d phi d theta. Okay, then there's something that goes here, and let's talk about bounds. Where does theta go between? 0 and 2 pi. Phi? Pi over 3 to pi over 2. Because, remember, I'm below the cone phi equals pi over 3, so I don't want anything in the top. I start at pi over 3, and I keep going to pi over 2, and then I stop, because I don't want to go anything below. Where does rho go between? 0 and 2, because I'm coming out from the origin, and I go out until I hit the sphere, which is sphere of radius 2. 0 and 2. So if I'm doing an integral, I'm going to have this integral where the box is what I'm going to integrate. Now let's talk about our density for a second. It says here that density is proportional to distance from the origin. When you see the word proportional, what does that mean? We haven't used it much this semester. Proportional, linear is not bad. Proportional usually means multiple of. There's like some constant. So that says our density is some constant times something. Well, proportional to what? The distance from the origin, which in spherical coordinates is rho. So that's our density. Density is k times rho. Turns out k won't matter. It will cancel out. If you just said k equals 1 and just said density equals rho, we probably would still give you the same full points. I don't know, because this is not the question we're asking. I want to do that to you guys. I want to make sure you guys get nice, fresh questions. That's what you guys want. Okay, so we know how to set up our basic integral. We just need to know what is it we actually need to integrate in. So let's talk about our center of mass. One of the things it says here is use symmetry where possible. Can we say anything about our center of mass right away? Yes, what can we say right away? Yeah, the z-axis, there's nice rotational symmetry here. So the center of mass is on the z-axis. Well, if it's on the z-axis, what does that say about our coordinates for the center of mass? Yeah, the x and the y are 0, and we only have to figure out the last piece, the z-bar. Okay, so how do you figure out z-bar? Well, you take a moment, this one, and then you divide it by mass. So it's the moment divided by mass. Now for mass, what will we integrate? Well, we integrate density, and so we would integrate, namely, k rho. So k rho, that's what would go into the box. Because there's always the famous question, what's in the box? What's in the box? Well, for mass, it's k rho. Now, what about for the moment? What would we do? We'd integrate zk rho, right? But there's one small problem. Z is not in spherical coordinates. So what do? So what is z in spherical coordinates? Rho cosine phi. So now, that's what goes into the box. And so you put that in the box. And now, you integrate those two, take the ratio, and boom, there's your answer. 0, 0, 2/5. You can do it in your head. So, no. It just turns out to be nice numbers. I remember. Don't always count on nice numbers, but we try to give you nice-ish numbers. Okay, but the rest of this is just computation. And in the interest of giving you a variety of problems, we will skip computation. You can see the full answer online. Just the solutions are there. Okay, staying in spring 2010 was a good year. Okay, here we go. Apply Green's theorem to evaluate the following. We have the integral around the curve, e to the x squared plus y dx plus sine of y cubed plus x squared minus x dy, where, whoops, typo, that's supposed to be c. C is the triangle with vertices 0, 0, 1, 0, and 1, 2 traversed in the counterclockwise direction. Okay. Well, you would first say, can we integrate something like e to the x squared? No. But maybe we don't have to. Maybe we have a theorem. Now, on this problem, what theorem should we use? Yeah, because it was kind of blatantly obvious. We will try to make it more subtle. We will try to sort of say, we're not going to like wave a red flag saying, use this idea. Because one of the things is we want to say, do you know when to use ideas? Other than when we blatantly tell you. So think about a problem. I know you're like, I've only got 50 minutes. I gotta just jump into doing computations right away. If you can take 10 seconds to think, I wonder what tool gets used here. Oh, that's right. There's this really nice tool. Wow, this is a fun problem. I like this one. Okay, so we're going to use Green's theorem, which says what? Well, we have our points, 0, 0, 1, 0, 1, 2. And we are traversing them in some counterclockwise fashion. And okay, so we notice, of course, Green's theorem, add a little bit of green to our picture, is here, says, look, this curve is bounding a region, and lo and behold, our integral will be the integral over our region, we'll clean that up in a second, of what? Well, we have our two pieces. This would be what we would call m on this part, this would be n. What goes here? Yeah, partial n, partial x. So what's the derivative of n with respect to x? 2x minus 1. Then come here and we do what? Yeah, and do I add or subtract? Subtract. Partial n, partial y, 1. Now, one of the hints should be like, the really terrible things should disappear. So that can give you a clue of like which derivative you need to take. Assuming we put terrible things on there. We like to put terrible things on there because it's sort of like fun. We like to intimidate students a little bit, make them unnerved, make them, get them off their game a little bit. But okay, integrate over our region, 2x minus 2. Now, the only other thing is, of course, figuring out what are the bounds. Well, so this is a pretty straightforward region. Definitely we don't do polar here because nothing's curvy. Polar works great for circles. No circles here. So, all right, do you want to integrate? We'll do dx dy or dy dx. Anyone have a preference? Dx dy? Okay, someone has asked for a dx dy. So this is part of a, hey, make sure you know how to get your bound set up. So let's think about dx dy. Well, outer layer, where does y go from? What's the least value for y? What's the largest value for y? 0 to 2. Now you do x. Where does x go from? Well, so here, the idea is, just think of a typical value for y. You run in between two curves. So, for x. So the higher value is pretty easy. That's where x equals 1. So that's not hard. This line we have to think about. Well, what's the line that goes from 0, 0 to 1, 2? What line does that? Y equals 2x. But notice these are x bound, so I don't want y equals 2x. I want x equals 1/2 y. So 1/2 y up to 1. And then the rest of this is computation. So you can read that on your own time. All right. Okay. Well, only 5 problems left to go. We can maybe make a little bit of headway. Use the change of variables, u equals x plus 2i, b equals x minus 2i, to evaluate this integral, 3x plus 6y quantity squared dA, where S is a parallelogram with vertices at 2, 0, and 0, 1, and negative 2, 0, and 0, negative 1. So I've got a nice looking parallelogram. Here's my region S. There we go. All right, so we're going to switch bounds. So integral S 3x plus 6y squared dA. This is going to become a new integral. Let's just work our way through it. Let's talk about our function first. Is there a nice way to take our function and rewrite it in terms of u and v? For example, 3x plus 6y, that looks really familiar. It looks a lot like u. It's 3 times u, right? So this is 3u quantity squared, or 9u squared. So that's obtaining the function. Okay. And then, well, we have to work for the rest. Okay. Let me just make some observations here. This line here is what? Well, it's the line x plus 2y equals 2. It's not too hard to check. But it's true, you can, because it satisfies this point and it satisfies that point. And on the other hand, this line over here is x plus 2y equals negative 2. And on the other hand, this line would be x minus 2y equals negative 2. And this line here would be x minus 2y equals positive 2. So I'm taking my 4 sides to my parallelogram, and I'm just rewriting what the bounds are. What are the curves that bounds them? So I haven't done anything very fancy yet. Now comes the fancy. Is there another way to write x plus 2i equals 2 using u and v? Yeah, u equals 2, which says that this will become a bound, u equals 2. How about x plus 2y equals minus 2? U equals negative 2. X minus 2y equals 2? V equals 2. X minus 2y equals negative 2? Equals negative 2. So it tells me that in terms of the UV plane, I'm going from u equals negative 2 to u equals 2, v equals negative 2 to v equals 2. So then the UV plane, I'm going over a nice square, which tells me my bounds are negative 2 to 2, negative 2 to 2, and doesn't matter which order I go, du, dv, dv, du, either one. You'll notice I've left a gap. Now either that's bad planning, or there's something that needs to go in the gap. Jacobian. All right. So the way that we taught you, there's other ways to do it, but we'll do it the way we taught you. We'll notice here a few things. If you add u plus v together, you get 2x, which tells you that x is 1/2 u plus 1/2 v. On the other hand, if you subtracted u minus v, you get 4y, which tells you that y is 1/4 u minus 1/4 v. So to do the Jacobian, you would take xu, xv, yu, yv, these various pieces here. These are partial derivatives. Derivative of x with respect to u is 1/2. Derivative of x with respect to v is also 1/2. Derivative of y with respect to u is 1/4. Derivative of y with respect to v is negative 1/4. And if you work this out, you get minus an eighth, which is negative 1/4. So that's the Jacobian. What goes here? The absolute value of that, which is 1/4. Now it's set up, and finish it out from there. Okay, so that was the hard part. All right, here we go. Given the vector field f of xy is cosine of x plus y plus e to the y, and that's in the I direction, and e to the y plus x j. And the curve C is parameterized by x equals pi halves cosine t, and y equals sine t, and 0 to less than or equal to t, less than or equal to pi. Compute the following line integral. Okay, well, this is an integral f dot dr. What are we hoping for? Yeah, we hope that this is something gradient of f dot dr. Okay, well, there's our question. Is this conservative? Well, instead of trying to check, it's usually just as fast just to come up with it. Okay, so if this was conservative, my function f, little f, x, y, the derivative with respect to x would have to be cosine x plus y. Well, okay, so integrate. Integral of cosine x plus y with respect to x would be sine x plus xy. Plus some other stuff possibly to make sure I get the right derivative with respect to y. So if I integrate this with respect to y, what would I need? Well, I need an xy, and I have an xy. What else would I need? I'd need an e to the y. And there I go. Yay, conservative. Now, if you're not comfortable with that, there's algorithmic ways to compute this. Other things you can do is you can say, this is what I think it is, and here I took the partial derivatives and they match. Okay, but now that I have this, lo and behold, that says this is not a hard problem because I take my function, sine xy plus e to the y, and then I do what? Yeah, I evaluate at the endpoints. My endpoints are, well, the start is I plug in 0. So I plug in 0, I get pi halves times cosine of 0, which is 1, and sine of 0, which is 0. And then I would get what? Well, plug in pi. Cosine pi is negative 1, so negative pi halves, and sine of pi is 0. And then just evaluate. And then you're done. Okay. Reverse the order of integration of this integral. So sometimes you have an integral, and it's like, it's a double integral, but the current integral looks terrible. We do that sometimes. We give you things which look terrible because we say, aha, if you apply the tools, then it's not so bad. Okay, well, let's think about what this shape looks like. We know 0 less than or equal to y less than or equal to 4, and square root of y less than or equal to x less than or equal to 2. Now, square root of y less than or equal to x, that's x equals square root of y. What do we also know that by? Y equals x squared. So if it helps to sketch, go ahead and sketch it. Y equals x squared. Okay, now we're told that y goes from 0 up to 4, and then we're going from square root of y over to 2, which means we're looking for this piece here. So that's our region. All right, well, if that's our region, for part A, we reverse the order of integration, means the function doesn't change, because the function doesn't depend on how we describe the region. What we're changing is the way we integrate. So we're going to integrate dy dx. All right, so work on the x bounds. Where does x go from? 0 to 2. Okay, good. Now we come in. Where does y go from? 0 to x squared. And off you go. And then you can finish it from there. That's part A. Part B, ... All right. Now, suppose you have this one. F is equal to x minus yzi plus y minus xzj plus e to the xy plus z squared k. And S is the surface. Z equals x squared plus y squared. Well, I already told you we would give you the pictures. But do you recognize that one? It's a bowl. If it was x squared plus y squared equals a fixed number, that would be a cylinder. If it was z equals the square root of x squared plus y squared, that would be a cone. Z equals x squared plus y squared is a bowl. And it's actually a bowl with the rim. Because notice I have a z less than or equal to 4. So there's an edge here. There's an edge to this bowl. Well, that should tell us that we should use Stokes Theorem. But guess what? They also tell us to say use Stokes Theorem. we will not always be this blatant about it. So use Stokes Theorem to evaluate this integral where n is the upward pointing unit normals, which means that the normals are pointing up. Now, in the last 3 seconds, what would we do to solve this problem? We would, instead of working with that surface, we would work with that surface. It's a better surface, and then lo and behold, we do the normals, n is straight up, 0, 0, 1. And from there, this curl will be super easy. Remember that z is equal to 4, and then it works out really slick. And things will work out pretty slick with Stokes Theorem problems. All right. Good. Good luck. Study hard. See you on Friday.